Hey chat! In this video, I'll go over how one might do a quantitative analysis using a UV visible spectrometer. This spectrometer uses UV or visible light to do the analysis, so it's very helpful in quantifying colored solutions. For this video, I'll use blue dye as an example. We can reliably do analysis for dilute concentrations of colored solutions. Since I don't know what concentration range I should work with for now, I'm going to prepare several standards through serial dilution. I'll dilute 500 microliters of dye to 25 milliliters, and keep doing that to have an idea of the ideal concentration range. Since this is not a pure chemical, I'll use a concentration unit called microliters of dye per milliliters of solution. When I pipette out 500 microliters and dilute to 25 milliliters, I'm applying a dilution factor to the concentration of 0.5 ml per 25 ml. The equation we'll use is called Beer's law. It says that the amount of light absorbed by a sample is directly proportional to the concentration of the absorbing species. The constant A is the intrinsic value of the analyte to absorb a particular wavelength. We call this absorptivity. The constant B is the path length the light has to pass through. The longer the distance the light has to pass, the more of it is absorbed. Since this is a linear equation in the form y equals mx, if we apply a dilution factor, the absorbance should also change linearly with the dilution factor. We'll see if this is truly the case later on in this video. I can then make multiple concentrations, measure their absorbance, and generate an equation of a line. To transfer the dye, I'm using a micropipette. These micropipettes have disposable tips and are calibrated to be useful if you're dealing with volumes less than 1 milliliter. To pipette out your desired volume, adjust the dial and press to the first stop before submerging the tip. When releasing the contents, press to the second stop to ensure that everything is released. After I prepare my multiple dilutions, I'm going to transfer to read the solutions in the spectrometer using a cuvette. Cuvettes are made with special glass to prevent drastic absorption of UV visible light, and they have a defined path length. The sides of this cuvette are frosted, and I could only hold it here so I would not damage or dirty the front and back of the glass where the light will pass through. This is a double beam spectrometer which accepts a blank at the same time as the sample. I've gone ahead and placed my blank in another cuvette, and this ensures that the reading has taken into account any absorbance from the solvent and other factors. The first thing I will do is to scan the wavelength which yields the highest absorbance. We call this the lambda max. Since the color is blue, this sample absorbs the complementary color orange. So, the lambda max should be between 590 and 630 nanometers. The spectrum of the UV vis showed a peak at 6 to 8 nanometers. So this is the wavelength that I will be using. I then set my wavelength to that value and start measuring my standard solutions. Because I'm dealing with liquids, I have to rinse the cuvette 3 times before reading. I'm also taking care not to have anything that will obstruct the light. The inside must not have any bubbles, and if I need to wipe the sides of the cuvette, I'm using a special type of delicate wipe and I'm just tapping, not rubbing, to clean. If I plotted my data, the plot isn't actually a straight line. Beer's law is what we would call a limiting law, which means that the equation A equals ABC is only true up to some point. It's only true for dilute solutions. The line starts curving at high concentrations. I'm aiming for absorbance readings around 1 and below. I was able to figure out that one of my standards had an absorbance reading of 1.306, so I prepared new standard solutions from this standard. Here is my new plot. Constructing a plot and equation of instrument response versus standard concentration is called making a calibration curve. I used a spreadsheet program to generate this line of best fit, and the R-squared value is very close to 1, which is ideal in chemical analysis. This is where the Beer's law concept comes in, because this line should correspond to A equals ABC. Although we have an intercept, the value is so small and this arises from uncertainty in our analysis, so we should still keep it in. With my calibration curve, I can now read the absorbance of unknown samples and use the equation to calculate for their concentration. Convenient, right? I need to emphasize, however, that we can only use this curve for absorbance values included in the curve. If we were to extrapolate concentrations, we might actually be assuming that the curve is still linear at that concentration. As what we saw earlier, the curve starts bending at a high concentration. Always dilute your samples if the absorbance goes beyond the standard solutions. I hope you were able to gain a good overview of how a UV visible analysis would work in a laboratory. As long as an analyte absorbs in the UV or visible region allowed by a spectrometer, you can construct calibration curves and calculate for the concentration of unknown samples. I'll see you next time.